Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with chapter 6 of microwave engineering and a family of microwave bipolar transistors we are dealt with. So the basic details of the microwave bipolar transistors we are covered: amplification phenomena, the operating principles, various configurations, power frequency relations. We address heterojunction BJTs also, JFETs we are also covered with, and now we have addressed the MESFET, the metal semiconductor field effect transistor, and to look at the equivalent circuitry and the computation of the drain current, let us have a simple problem. So here we are provided with a problem statement. A typical N-channel gallium arsenide MESFET has the following parameters. The parameters have symbolic notations denoted. Nd is equal to 8 into 10 raised to power 17 per centimeter cube. A is equal to 0.1 micrometer. Epsilon R is equal to 13.1. L is equal to 14 micrometer. Z is equal to 36 micrometer. Mu equal to, we have the representation 0.08 meter square per volt second, or in terms of centimeter square per volt second we can use 800 directly. Vd, the voltage is 5 volts, and we have the Vg minus 2 volts. Vs, the velocity 2 into 10 raised to power 5 meter per second. Now we are asked to make calculations for, in the part A, the pinch off voltage, in the part B, computation of velocity ratio, in the part C, determination of saturation current provided Vg is equal to 0, and lastly to determine the drain current Id. So all this for the MESFETs here, considering the knowledge of equivalent circuitry and the drain current. Very first of all, we shall be identifying the given parameters. The very first parameter is denoted by Nd. So here we mention the Nd, nothing but the electron concentration. So here we have electron concentration value is equal to 8 into 10 raised to power 17 per centimeter cube. The next parameter is a measurement of length, and for the MESFET it is nothing but the channel height. Here in this problem statement, the channel height is represented by small a, and it has the value 0.1 micrometer. Next to that, the very common, we have it useful, that it is nothing but the epsilon R here, the relative dielectric constant, that is holding the value 13.1 here. Another measurement of length, a dimension for the given device, that it is L. So it is nothing but the length of the channel. I mention channel length with the given value 14 micrometers here. Another dimension of the device we have by the representation of Z here. So Z is nothing but the channel width. So the channel width value we have here, that it is 36 micrometer. After these dimensions of the device, we have the representation of mu. So mu is nothing but the mobility. Here the charge carrier is the electron, hence I write electron mobility. And the second representation form, I mention here that it is 800 centimeter square per volt second here. After that, a voltage value is provided to us denoted as Vd, and this D stands for the drain. Hence I call this the drain voltage value, and it has the given value that it is 5 volts. After that, another voltage Vg is provided. It is nothing but the gate voltage for the given MESFET. So it has minus 2 volts as the magnitude. And lastly, we are provided with a kind of velocity denoted as Vs. It is nothing but the saturation drift velocity. So saturation drift velocity Vs is equal to 2 into 10 raised to power 5 meters per second. So with these given details, we shall be finding the answers for part A to part D here. So in the part A, we require the pinch off voltage. So pinch off voltage can be denoted by Vp, and it can be computed for the given MESFET by Q into Nd into A square divided by twice epsilon S. So we have all the values. So here we compute Vp by the next step as substituting 1.6 into 10 raised to power minus 19 as Q into, here we have concentration 8 into 10 raised to power 23 into, here we have 10 raised to power minus 14, and this is all divided by, we have twice ES, hence 2 into 8.854 into 10 raised to power minus 12 into 13.1, the relative dielectric constant value. This gives us the pinch off voltage value Vp is equal to 5.52 volts. So I underline this particular value as the answer for part A. So here in the part A, we are finished with calculation for pinch off voltage. Now we require the value of the velocity ratio. So for part B, the velocity ratio we denote by the symbol eta here, and it can be simply the numerator represented mu into the mod of Vp divided by the Vs in multiplication to the capital L. So making a substitution of values here, we get the numerator 0.08 in terms of meters per volt second. We take the mobility here in multiplication to the mod of Vp that we have obtained, the magnitude 5.52 we use, it is divided by Vs is 2 into 10 raised to the power 5 into the L value is 14 into 10 raised to power minus 6. So these are the substituted values into the formulation. Therefore, the velocity ratio eta we obtain with the answer 0.158. So this answer I outline for part B here. As this is the ratio, it don't have any kind of measurement unit. So after computation of the velocity ratio in part B, we require the determination of saturation current provided the gate voltage Vg is equal to 0. So for obtaining the saturation current at Vg is equal to 0, for part C, we represent the current by capital I suffix P, making use of the formulation. The numerator is Q into Nd into mu A Z into Vp, and this is all divided by thrice capital L. Substituting the values, Q is 1.6 into 10 raised to power minus 19, Nd is 8 into 10 raised to power 23, mu is 0.008 into A value is equal to, we have 0.1 micrometer, so we put 10 raised to power minus 7. The Z value here we have 36 into 10 raised to power minus 6, and lastly Vp, the obtained value is 5.52. So this is all divided by the denominator. Here we have 3 as it is, and the L value is 14 into 10 raised to power minus 6. So the calculation gives us the value of saturation current IP is equal to, here we get 4.845 into 10 raised to the power minus 3. As this is the current, the measurement unit should be amperes. We represent it in terms of milliamperes as IP is equal to 4.845 milliamperes. So I outline this answer. So here we are covered with the answers for part A, B, C. In the last portion D, we require finding the drain current ID in total. Now for determination of total drain current into the part D, we first of all make the computations of mu. So the mu will be, we have Vd added with mod of Vg divided by Vp. This is to be having the power 1 by 2, so it means it is in the square root. So the substitution gives 5 plus 2 divided by 5.52 in the square root with the answer 1.126. For computation of the total drain current, we require mu square, so mu square becomes 1.268, whereas mu cube is also required, it becomes 1.428. So these are the helpful values. Along with mu, we require another parameter to be used in the calculation of drain current, that is nothing but the rho. So rho is computed as mod of Vg divided by Vp kept under square root. So here making the use of Vg equal to 2, the magnitude Vp is equal to 5.52 obtained under square root gives the value of rho is equal to 0.60. Therefore rho square is equal to 0.362 and rho cube is equal to 0.217 we have obtained. So making the uses of mu square mu cube, rho square rho cube, we proceed. Finally, the drain current we write by the expression ID is equal to IP. The numerator next to the IP is 3 in the bracket mu square minus rho square minus 2 in the bracket mu cube minus rho cube. In the denominator we have 1 plus eta in the bracket mu square minus rho square here. So substitution gives the RHS by the next step, 4.845 into 10 raised to power minus 3 into 3 in the bracket 1.268 minus 0.362 minus, here we have 2 in the bracket 1.428 minus 0.217, and this ratio is divided by, we have 1 minus 0.158 in the bracket 1.268 minus 0.362. So this gives us drain current ID is equal to 4.845 into 10 raised to power minus 3 into 0.259. So finally the drain current ID is obtained as 1.26 into 10 raised to power minus 3. So it should be in terms of amperes, or we can also express ID as 1.26 milliamperes. I have outlined this answer. So this way we are covered with the answers from A through D for the drain current and the equivalent circuit of the MESFETs here. By the next lecture we shall be addressing the cutoff frequency and another kind of frequencies for the same device, metal semiconductor field effect transistor. I hope you are definitely benefited by the knowledge we share for microwave engineering subject. For more knowledge and the details, you can subscribe to Ekeeda channel. Thank you.